So welcome back, everybody. We're going to continue on with our work in lesson 5 on failure mechanisms. And we're going to move away a little bit from static stress states, which were the primary emphasis of our previous portions of this lesson when we talked about fracture and even strain rate effects. We're going to move into a phenomenon called fatigue, which is basically cyclic loading of parts. And if you give it some thought, the fatigue tends to replicate more of what we see in service with parts. And we're going to find that fatigue's a rather important consideration when designing and inspecting, and in your work lives, you're going to run into fatigue issues on a continuous basis. And so we're going to get into fatigue a little bit. I'm going to show a few issues that have been encountered with fatigue. Some ended up in failure, some ended up in tragedies that occurred. But I think from what we can look at with all of these is what we've learned about fatigue and a little bit of what we still don't know. So we're going to move on, as we do with all of our lessons, into our sort of quote for the day. Arthur C. Clarke wrote a little novel and he made it into a movie called 2001: A Space Odyssey. So it's back in time a little bit, but I tend to like what he says here about the difference between the art of the possible and the art of impossible. He uses an elderly scientist as sort of the tool for that type of thought. So more into what we're going to be talking about today is fatigue and cyclic loading. And what we're going to see is when we represent fatigue on some type of curve, sort of like we saw with stress strain curves, fatigue tends to be represented on a different type of curve. It's what's called an SN curve, where S will represent the stress amplitude and N will be the number of cycles to failure. And we'll look at sort of crack initiation and propagation of what drives fatigue, but really probably the important things from a design standpoint are what are the factors that affect fatigue life? What can we do as far as design or service or anything like that to be able to enhance fatigue life and in a lot of cases maybe mitigate the potential for fatigue? So we see not a lot in Callister. I'm going to spend a little more time than Callister did on this topic, and see 4 additional problems. So the 2 with asterisks, as always, are part of your homework assignment due with this lesson. But as always, I recommend that you also run through the other practice problems. You might see something like that on an upcoming exam. So what we're going to see is there's a number of different terms. So fatigue is really it's really a good way to look at fatigue is it's a new subject from fracture that we looked at before. And so we're going to have to define a couple other things. Fatigue strength and fatigue life are linked. So whenever somebody discusses fatigue, I will start on this now and we'll move on as we go. But you cannot just give a given number for fatigue strength. You also need to take into account what fatigue life is. And so it's always a material or a component has a fatigue strength of X megapascals or X KSI at a life cycle of so many units, which we usually look at in 10 to the third, 4th, 5th, 6th type of thing. We're going to find out, you might call it an endurance limit, but a lot of materials below certain stresses will not demonstrate fatigue. And so this idea of a fatigue limit becomes very important as we start looking at different materials. And we're going to see that low cycle, high cycle fatigue depend on the number of cycles to failure and how those are determined and how they will impact the way we look at design components for that. So a lot to think about with fatigue, some new terminology, but we'll start with what is fatigue. Really, it's a dynamic and fluctuating stresses. So if you think about it, most structures do not see a uniform stress. We turn things on and off. You imagine an airplane, it goes into different weather conditions, different flight characteristics, whether takeoff, landing, cruising, climbing, descending. All of these things put different stresses at different parts of that large structure. And during fatigue, and I will say this, that failure can occur at a stress level considerably lower than the tensile yield strength of what we see for a static load. And this is what makes fatigue something that we really need to pay attention to, is that failures are occurring below where our design stresses were. And so it has a real impact on how we design things. And it's the single largest cause of failure in metals, approximately 90%. If you think about that, you probably say to yourself, why aren't we looking at this almost exclusively? That's a little bit sort of limited for this class, but it's something that you need to take into account as you start really going into your professional lives, which are going to start sooner than you think. Most fatigue failures are brittle, so they're going to represent some type of, there's no plastic deformation. Since the initiation and propagation of the cracks, especially the propagation, can occur rather rapidly, it's sometimes really difficult, even with an inspection regime, to determine when they're going to happen. And this is always the big one. Failure is catastrophic and occurs with little to no warning. Now we're going to see an example of that here. What are the sort of the consequences of fatigue? This is simulation, but in 2007, the Air Force ran into, really, you would look at it as a crossroads or a major issue. F-15Cs at the time and now, even with other aircraft coming online, are still the primary interceptor. This is a fighter jet that we're talking about here. And so the Air Force ran into some issues because there were two incidents. One occurred over Utah, the other one occurred over Iraq at that time, where planes came apart in mid-flight with no warning. And we'll see an example of what happened. And so what we see here is the animation, the plane, he basically leveled out after a turn, and the plane separated in two. In this case, in both cases, actually, the pilots were able to eject. There, he's going to go there. That was the ejection seat in the simulation going. And we can see here, it's just normal flight operations, and the aircraft broke in two. And at that time, after the second one had happened, the Air Force literally grounded every one of these airplanes. And so every this model to try to figure out what happened. And so they picked up the debris, went and did a failure analysis. A lot of what we had found, started looking at all the aircraft. So they had a pretty good idea where the failures occurred, whether it was from the pilot talking to them or from debris they had maybe found on the ground. Because in most cases, these planes weren't out by themselves. There was, what you might call a wingman or a second aircraft there. And so that pilot had to look at what had happened to that aircraft. But when they started really looking at it, they started finding that they were finding fatigue cracking in what they call a longeron. This is a primary structural component. And it's from the name longeron, they're longitudinal members. And so they were transferring skin load into the internal structure so that the plane would, for the most part, stay together. Now, when they started failing, you can see how their load was transferred into the internal structure. It would lead to a failure. But it was a fatigue crack over time. Now, the thing to remember with these aircraft is that they're a little older than you might imagine. Most of these F-15s were built in the 1970s, 1980s, and so they have a lot of flight time on them. And in a lot of cases, they're going well beyond what their estimated original life cycles were. And this is where fatigue really starts to come. We saw it initially in the first class with the Aloha Airlines flight, where there was a combination of corrosion and fatigue on a door that led to a fuselage separating from the skin, this aircraft skin basically separating from the fuselage. And so something, this is different, but it was a fatigue failure. Now, to hammer the point home a little bit, if we go back, the deadliest air disaster in American history happened in 1979 at Chicago's O'Hare Airport. And this came down to a fatigue failure as well. It was a DC-10 at the time. And on takeoff, that is the engine, components of the engine sitting on the runway at O'Hare. So as they started their ready to hit takeoff speed, the number one engine, which is the engine on this side of the aircraft, literally came off. And it took a portion of the leading edge of the wing with it. And so with that, the pilots had no control of the surfaces. And so the plane went down and all on board perished when the flight. And so this is a photograph of the plane as it was right before it crashed. So what led to it? And I think, as far as a lesson goes, this is one thing, especially as engineers, that we can take away from something like this. And what we tend to see is unauthorized maintenance procedures. They led to fatigue cracking on the engine pylon. Now, this is one area where American Airlines, it's a DC-10, so it was an old McDonnell Douglas aircraft. This was meant to be the competitor to the 747. It was a rather large aircraft. A number of them had been sold. There were some issues with this aircraft. This was not the first crash of this aircraft class. They had a problem with a cargo door on the back failing and coming off. But this was the first time they ran into this issue of something as catastrophic as an engine separating from the aircraft. Now, when they had to do maintenance and replace the engines, which is pretty commonly done on commercial aircraft of this size, they were required to basically remove the engine. And so there was a very long and involved procedure for removing the engine. Now, American Airlines thought they had developed a workaround and saved them over 200 man hours. And as industrial engineers, which a lot of you are, that is a pretty big savings. And so they took the manufacturer-approved procedure and they trimmed it down. And so what they wanted to do was hold the engine in place. And in this case, they used a forklift to hold it. United Airlines flew a number of these aircraft as well, and they did not like the maintenance procedure. They took a little different approach, which ended up not causing the type of damage that we saw in the American Airlines flights, where they actually strapped and used an overhead crane to hold the engine in place. So you can imagine with a forklift, what was happening is they were pulling the engine in and out with the forklift. They kept running it into these pylons. And so what they were doing was they were creating surface flaws in them, especially as you can imagine running into that engine pylon with a forklift. And so a fatigue crack started to develop. And so over the next 8 weeks after it was in maintenance, this fatigue crack got larger and larger. And so at full takeoff thrust, the engine, for the most part, it overloaded, failed, and the engine broke off at that point. And so it gives you an idea, and this is something that we'll be moving into as we go into the lesson, is that fatigue can in a lot of cases be a surface-driven phenomenon. So surface defects, machining defects, when we talked about hardness indents, different things like that, these all can lead to fatigue under the right types of conditions. And this was an example of that happening.